We just derived the formula for the inverse tangents derivative. Let's take a look at the rest of the derivatives of the inverse trig functions. And we're going to state the theorem in the most general form, which that involves using the chain rule. Let's suppose that u is a differentiable function of x. We had just seen previously, for example, that the derivative of the arc tangent of x, or tangent inverse, was 1 divided by 1 plus x squared. If we have a differentiable function of u on the inside, then that derivative, for example, would be like 1 divided by 1 plus the inside part squared. And then from the chain rule, you would multiply by the derivative of the inside, which would be u prime. Okay. The arc cotangent has a similar derivative, but simply with a negative sign. And if you go ahead and if you look at these 6 derivatives, really it's kind of not as much to memorize as what you might think. It's always kind of easy to kind of pair them up. Pairing up arc sine with arc cosine, arc tangent with arc cotangent, and arc secant with arc cosecant. They both kind of have similar formulas. The only difference being the sign. And to remember which one has the negative sign, if you forget the arc part, again, as we saw with when we did the regular trig derivatives, if the trig function starts its name with a c, so like cosine, cotangent, cosecant, it's going to have a negative sign in its derivative formula. If the trig function does not have a c in its name when it starts, like arc sine, so sine, tangent, secant, they don't have c's, so their derivative will be positive. And then you can kind of see the formulas for each of these. The derivative of the arc sine of u is 1 over the square root of 1 minus u squared times u prime. The arc cosine of u would have derivative negative 1 over the square root of 1 minus u squared times u prime. Derivative of arc tangent we've already seen. It's 1 over 1 plus u squared times u prime. Derivative of arc cotangent is negative 1 over 1 plus u squared times u prime. And then for the derivative of the arc secant of u, it's 1 divided by the absolute value of u times the square root of u squared minus 1. And the derivative of the arc cosecant of u is the negative of 1 over the absolute value of u times the square root of u squared minus 1 times u prime. Okay. Let's go ahead and see if we can find the derivatives in example 4. We want the derivative of the arc sine of 2x. According to our formula from above, the formula for this should be 1 divided by the square root of 1 minus the argument of the arc sine squared. So if we have a u on the inside, we're doing u squared. Well, here we have a 2x on the inside, so it's going to be 2x that goes here. And then from the chain rule, it's not just a simple x on the inside. We need to multiply by the derivative of the inside function, and that's going to be 2. We can simplify this a little bit. We're going to have 2 in the numerator. This is the square root of 1 minus 4x squared. So the derivative of the arc sine of 2x, that's 2 divided by the square root of 1 minus 4x squared. Let's take a look at the next one. The derivative of the arc tangent of 3x, that's going to be 1 divided by 1 plus the argument of the arc tangent squared. What we have on the inside is 3x, so it's a 3x that goes here. But then from the chain rule, we need to multiply by the derivative of the inside function. The derivative of 3x is going to be 3. Simplifying this, we get 3 divided by 1 plus 9x squared. So 3 divided by 1 plus 9x squared. Let's take a look at another one. In example 4, we have d dx of the arc sine of the square root of x. This is equal to 1 divided by the square root of 1 minus the inside part, which is the square root of x squared. And then from the chain rule, we need to multiply by the derivative of the inside function. We know that this is x to the 1/2, and we've seen that derivative a bunch of times. But the derivative of the square root of x is 1 over 2 squared of x. Okay. So we get this. This is equal to, we have a 1 divided by, we have 2 square roots of x, and then we have another square root of x here, where on the inside, we're going to have 1 minus the square root of x squared is just going to give us x. So this is good. We can leave it like this. If you wanted to combine the square roots, you're more than welcome to do that. You can bring them all under one parenthesis, and it would be x times 1 minus x. Let's take a look at the derivative of the arc secant of 2x. So the formula for this, if we go back, d dx of the arc secant of u, this was equal to 1 divided by the absolute value of u times the square root of u squared minus 1, and then from the chain rule we would need to multiply by the derivative of the inside, and we call that u prime. The book kind of puts it in the numerator. I kind of like to write it out like this because it kind of lets you see the pattern and the part that's a formula for the arc secant while keeping the chain rule part kind of out and away from it. So here we have the arc secant. We want to find its derivative, and the argument is e to the 2x. This will be equal to 1 divided by the absolute value of e to the 2x times the square root of e to the 2x squared minus 1. And now from the chain rule, we need to multiply by the derivative of e to the 2x. The derivative of e to the 2x is going to be e to the 2x. And another chain rule application, the derivative of the exponent would be 2. Okay. So here's what we get. We have a 2 e to the 2x, which I can put in the numerator, divided by, now this is something to kind of keep track of. Typically, when you do most function derivatives in this arc secant, you would need to keep the absolute value bars. They're a part of the formula, so they would typically have to be there. However, if you look at the graph, or if you know a lot about the exponential function e to the 2x, e to the 2x is always positive. Therefore, the absolute value of e to the 2x is simply e to the 2x, because it's always a positive quantity. So we're in a nice situation where we're actually able to, because of the particular thing on the inside, we can get rid of the absolute value bars, so they're gone. Here we have e to the 2x squared, that's a power to a power. That's going to give us e to the 4x minus 1. And then from there we can cancel these guys out, and we get 2 divided by the square root of e to the 4x minus 1. So there you have it. The derivative of the arc secant of e to the 2x is 2 divided by the square root of e to the 4x minus 1. Okay. Let's take a look at example 5. We want to find another derivative here. We have the function y equals the arc sine of x plus x times the square root of 1 minus x squared. And because we do have a square root function here, let's just take one preliminary step to go ahead and rewrite it. And we're going to rewrite it with a fractional exponent. We're going to take our derivative, I'll call it dy dx, or y prime, doesn't matter. The derivative of the arc sine of x, we saw this from before, it's 1 divided by the square root of 1 minus x squared, plus, and now with this second term, this is a product. This is x times that square root, therefore we're going to need to use the product rule for this. We have two pieces, the derivative of x is 1, leave the second piece alone, plus now we have our x, and we need to multiply by the derivative of this expression. Well, that's going to be the chain rule. We're going to bring the 1/2 down, leave the inside part alone, reduce the power by 1. 1/2 minus 1 is negative 1/2, and then we multiply by the derivative of the inside function. The derivative of 1 minus x squared should be negative 2x. So what do we have? We have 1 divided by the square root of 1 minus x squared plus, this thing here is essentially the square root of 1 minus x squared. And now I'm going to have a minus, the 1/2 and the 2 cancel. We still have that negative coefficient coming from this part right here. We have x times x, which is x squared. And then we have this negative exponent here. I'm going to bring it down to the denominator, and I'm also going to go ahead and I will go back to the square root notation. Okay. So this is what we have so far. These two are like terms, so we can combine those. This is equal to 1 minus x squared all over the square root of 1 minus x squared plus the square root of 1 minus x squared. And if we look at what we have with this first thing, maybe I'll go back to the fractional exponents. This is 1 minus x squared to the 1/2 power. We could think of the numerator as 1 minus x squared to the first power. And that's simply division by like bases, which means that we're going to subtract those exponents. 1 minus 1/2 is 1/2. So this is 1 minus x squared to the 1/2 power plus the square root of 1 minus x squared, which is essentially the square root of 1 minus x squared plus another square root of 1 minus x squared. And when we combine those two, we get 2 square roots of 1 minus x squared. So the derivative of this function, so if we go for our y prime is equal to 2 square roots of 1 minus x squared.